Hello everyone. Welcome to the Amazon ML Summer School 2022. My name is Atul Sarup. I am a senior manager for applied science at Worldwide Search Amazon. I'll be leading this session on dimensionality reduction, which is one of my favorite topics in machine learning. Um, so the usual approach to building machine learning models, the supervised machine learning models, is to have data, usually lots and lots of data, and the idea is to predict a given label. And what you do is that you train the model to be able to predict the label while showing that you are able to achieve a very low error on a test data set. Now, this approach works extremely well when your feature set is not too large, typically for problems where you have numerical features being used for predicting the final label. But when you have problems like the labels have to be on the prediction has to be on the basis of textual data, it tends to get a little out of hand. So, for example, if you have a text classification problem of if this story is interesting or not, your features would be the bag of words representation. You tend to like sort of have one feature per word, and essentially what you land up with is that you land up with hundreds of thousands of features, one feature almost for each word in English language. And this is when you have not even considered like a bigram or a trigram set of features, right? So then the question becomes like sort of how do we solve this problem? Because essentially now you have data coming in. The problem is the same to predict a classification label, but now your learning algorithm is overwhelmed because of the multitude of features on which it has to learn the weights on, right? So, and also in many of these problems, what you would notice is that some features matter. So, let's say sort of in the text data, and you want to figure out if this is something that is relevant to babies or not. In case you have the relevant features would be like a diaper or a stroller or a bassinet or a cradle, right? Now the stroller may co-occur with terms like wheels or mobility or moving around, right? And then the wheels mobility related features may not be as relevant to the classification problem. So the problem becomes then to find out which features are important and which are the other ones that can simply be ignored. So there are two broad approaches for dimensionality reduction. One is to carry out feature selection, where essentially what you're doing is that you're downsizing the set of features that can be used for the prediction problem. The idea being that you want to remove these noisy or redundant features which are making your model not so predictive. Or you could have like sort of applications where you have a certain budget on the number of features. So these could be online applications where essentially adding number of features increases your latency overall in terms of the model evaluation. The other area is when you have applications that require interpretability. So let's say that sort of you have a problem where you're trying to, let's say, approve or disapprove the loan application of a certain applicant. And in such cases, you have to be able to explain, if challenged in a court of law, why a particular loan application was rejected. In such cases, you would require only a very contained set of features to be able to predict whether a loan application is accepted or not. The other set of methods of carrying this out is by reducing the dimension of your feature set into a low dimensional feature which you learn as a combination of the existing features, right? So this could be carried out by combining the words together. For example, in our text-based prediction problem. And these could be linear or non-linear in nature. So the linear models typically are the principal component analysis, multidimensional scaling, matrix factorization, t-SNE. These are the models that sort of we will talk about today. The other sort of set of models which have become extremely popular in recent times are related to representation learning, essentially learning embeddings. And so they've gotten so popular that now you have pre-trained models available which do extremely well for a variety of tasks. In these pre-trained models could be models like BERT, Excel and Robota, so in a lot of these which tend to work across languages and can help you solve very many number of tasks, prediction tasks. Coming to feature selection, there are three main categories of feature selection techniques. One, what are called as wrapper methods. These are where you use ML models in a sequential manner to be able to identify the subset of features that you should be using. The next set of techniques are filter methods, where you pre-identify some goodness scores for each of the features and then order them according to their goodness scores and use them. The third set of techniques that tend to actually sort of work the best are embedded methods, where you jointly optimize for loss and feature selection. And we will talk about these in the upcoming slides. In wrapper methods, the idea is to select the best subset of features that tend to perform the best. But however, this is an exhaustive search. Given n features, there are 2 power n possible feature subsets that can be constructed. And as you can see from the slide here, this 2 power n tends to blow up quite significantly and fairly quickly. Even for 30 features, the 2 power n combinations are over a billion. You can't think about like making a billion, training a billion models and then try to figure out which one is best out of those. So typically, greedy algorithms are applied to try and figure out these n features on which you should build your model. You could, for example, think about a sequential forward selection model method, recursive backward elimination method. You could use GAs and similar methods. So as far as sequential forward selection method is concerned, what you do is that you pick up one feature at a time. The one feature that at any given stage helps you improve the model performance by the maximum. So you start the process by having no features at all, and then you find that one feature that gives you the maximum predictive performance. After having found that one feature, then you add the next that in combination with the first feature gives you the maximum boost, and so on and so forth. And you end when you find out that adding any additional feature actually degrades the model performance as such. Okay. So then if you were to think about the feature selection as in terms of a graph where you have 4 features in this particular case, and for a particular feature place, 0 indicates if that feature is part of the feature set for prediction, and 1 indicates, 0 indicates that it's not part of the feature set, and 1 indicates that it is part of the feature set to be for prediction. So essentially what you're doing is that you are carrying out a search on this particular graph. And in case of forward selection, what you do is that you start from 0, 0, 0, 0, and then you pick up that feature in the first stage, which gives you the maximum predictive power. So let's say that after having evaluated these 4 combinations, you figure out like this one gives you the most predictive power. Then you, with that feature selected, you find out which is the next one that gives you the most predictive power. So then you find out that features 3 and 4, let's say, give you the most predictive power, and then you pick up the next and so on and so forth. And in this process, you identify at which point you should overall stop. Okay. The problem is that such a forward selection process is not necessarily optimal, because it's not guaranteed that you would be able to find the globally best solution. It is quite possible that having carried out a forward selection process, you should carry out a backward selection process as well, which removes features to be able to take care of any collinearity that may exist between the features that you have selected, thereby giving you a better performance than what you have achieved through a forward selection process as such. So as a thought exercise, I would want all of you to just think about, like, sort of what would a backward selection process do. Very similar to the one that we talked about in terms of forward selection, but just go back to the sort of graph that we had earlier, and then see what a backward selection process would do. The next set of methods are the filter methods, where essentially what you do is that you have a statistic, let's say sort of J, for each of the features, and you then try and figure out what is the goodness of that feature for a given feature. So for example, in this particular example, the goodness of features, let's say feature number 32 is 0.98, and then you order them in decreasing order of their goodness, and then you decide what your budget is. And let's say sort of in this particular case, you had a budget of 5 features, then you select the top 5 features according to the goodness of feature metric. And some of the goodness of feature metrics are things like mutual information, Pearson's correlation coefficient, or a chi-square statistic that tend to be popular, and they give you good estimates of which features are predictive of in the final model. Going a little deeper into these individual metrics, the Pearson's correlation coefficient is computed in this manner, like sort of the slide shows you how this is computed, but essentially what it tries to do is it tries to compute the linear relationship between any given numeric feature A and its target value Y. And the covariance matrix essentially captures the correlation between the final variable and the individual features. On the other hand, the mutual information gives you the correlation between a categorical variable and the class label Y. So that's why the popularity of these two methods. If you have a lot of numerical variables, you tend to use the Pearson's correlation. If you have a lot of categorical variables, mutual information comes in handy. However, these filter methods, what they don't take into account are what are called as feature interactions. And to give you an example, this is a toy example of how you could have two features, each of them independent of the label or the variable to be predicted, but when combined together, they can work together and predict the variable. So if you were to take let's say sort of the variable x, by itself the variable x is actually independent of y, and you can compute that by carrying out the exact computation of the mutual information as such, right? Similarly, the variable double x, you could similarly prove that it is completely independent of y. However, the interesting thing that happens is that when you combine these two variables together, so in this particular case, what we have taken is that we have taken the two variables xx and x, and we have constructed a new variable, which is the subtraction of the two. Individually, these two variables are not predictive of y, but when combined together in this particular format, a minus c and b minus d, for example, when the values of the new variable are a minus c and b minus d, you would see that sort of y comes out to be 1, otherwise it's always 0. Now the filtering methods are unable to discover this, so that's why they are shortcoming on being able to give you the best models as such. Okay, so at one hand, you can parallelize the computation of the goodness function or the goodness score, but at the same time, sort of the interactions are not captured, and then you would land up with suboptimal model selection process. Okay, so the third class of methods that we talked about were the embedded methods. Now, the embedded methods tend to sort of outperform the others usually. The principle behind the embedded methods is straightforward, that essentially you combine the feature selection as part of the model learning process itself. And I'll show you like sort of how that works out. So there are two popular sort of forms of this. One is called the lasso or the L1 norm version, and the other is the L2 norm version of it, or the ridge regression, so to say. Okay, so the L1 norm version, or the lasso, essentially what it does is that it takes the loss term, which is the first part. All of you must be familiar with this, the squared loss, right? So this part shows your prediction. This is the target variable, and this is showing you the squared loss. In addition, what you do is that you add the size of weights that you have on each of these individual features. Please keep in mind these are size of weights, not size of individual xi's, and that's what makes all the difference. On the other hand, in case you were to like sort of take the ridge regression form of it, what you do is that you replace the second term with the minimization of the squared forms. Now, so then just replacing the norm with the squared version of the size of weights actually tends to change the behavior of the optimization output. So while the L1 norm induces sparsity in features, it tends to force as many betas down to 0 as it can. The ridge regression doesn't do that. It tries to reduce the size of betas as much as possible, but essentially it doesn't drive them down to 0. And just to like sort of aid your intuition process, let me show you how that works, like sort of in a two-dimensional plane. So if you were to consider this optimization problem in a two-dimensional plane, so these red lines are essentially sort of showing you the loss, the squared loss term. So anywhere on this, on a particular red line, you have the same squared loss. That's the first term in your overall loss function. So in case of L1, what happens is that the blue sort of rhombus actually is giving you the second part, which is the sum of the mods of beta, and the red lines are showing you the squared loss, the first term. And essentially sort of this is the trade-off point at which like sort of the sum of the two losses can be minimized. Now what you would notice is that essentially the point that gets selected is the one where the isoloss term actually intersects with the axis. So in this particular case, the beta 1 ends up being 0, right? On the other hand, in case you have a like sort of the L2 norm version, in the L2 norm version, the second term looks like it's a circle in case of a two-dimensional sort of two-dimensional case or two-feature case. But in case you had multiple features, it will become a sphere. And essentially, the intersection is such that the beta 1 value, for example, is very small, but it still exists. It's not pushed down to 0. Okay. Yeah. So overall, like sort of Feature selection has multiple benefits. It sort of improves the overall accuracy of your models. It reduces the search space that the classifier has to search for in terms of like sort of the features being used. There is a reduced prediction time because lesser number of features are being used. Therefore, the classifier or the regressor can be much more quicker. And then, of course, from an interpretability point of view, there are fewer number of features to be interpreted, especially in the L1 norm case. The lasso sort of helps you out there. We now come to a topic which is quite advanced, and it was quite revolutionary when it appeared. t-SNE solved one of the like sort of very open problems, I would say, in multi-dimensional scaling, and sort of I'll just brief about what the overall problem is. So t-SNE, the motivation behind t-SNE is that we as modelers, as ML modelers, often are sort of faced with this problem, right? As in sort of what is the right technique to build a model on a given data? Like what is the structure behind the data overall? What are we looking at? What is the kind of problem that we have at hand? And essentially, in trying to do that, the best way that humans can sort of build an intuition around data is by visualizing it. Now, in case this data, if it were in 2 dimensions, it's easy for us to visualize, right? It's a fairly easy task. For a 3-dimensional, yes, you could probably build some like sort of fairly advanced visualization techniques, and especially sort of given today's AR technology and everything, you could potentially sort of AR, VR, you could potentially like sort of visualize this data quite well, right? But then we rarely have problems where you have you have 2 or 3 features at max. Usually these are much larger number of features. What happens when you have a 4-dimensional data, or you have an n-dimensional data to visualize? What happens then? So the natural choice or the method adopted is to make sure that you project your entire input data into a 2-dimensional space. Now that's an interesting concept, but how do you do that, right? As in sort of you have to make sure that a certain structure of the data is maintained. So essentially, to solve this problem, this is the approach that is taken. So essentially, if you think about it, the structure of the problem is the following: that you have been given as input a high-dimensional input data vectors, right? These, let's denote them by X. These are in very high dimension, capital N, let's say. And what you're trying to do is that you're trying to create a mapping for these high dimensional X for each of these data points. You're trying to create a Y. Y is a small n dimensional, is in the small n dimensional space, where small n is much smaller than your capital N. Okay. But we want to make sure that the mapping from X to Y follows certain rules, or sort of that the structure overall is maintained in going from X to Y. Okay. Now, so the idea of the stochastic neighbor embedding overall is that sort of we should get the local distances right. So essentially, if 2 data points are closer to each other in the high dimensional space, which is X, they should be closer to each other in the Y dimensional, the lower dimensional space, or Y. Thereby sort of the term local distance. But the other way around should be okay. Like sort of if a point is let's say sort of not so close in the high dimensional space, it is okay for it to be sort of projected as a small distance in the low dimensional space. So essentially, the way we model this problem is the following: that let us say that sort of we convert this problem of mapping, let's say sort of each data point in high dimensional space X to low dimensional space Y to an equivalent problem. the equivalent problem is that of some sort of probability of picking a neighbor. So essentially think about it this way, that let us say that sort of you have been given a point I in high dimensional space, and let's say P represents the probability of picking another point J in the high dimensional space, where sort of let's say J is in the local neighborhood. So essentially the first term that you see over here, the Pj given I, essentially denotes that. A similar term in the lower dimensional space can be computed similarly in here, just that sort of I think the lower dimensional space is normalized, so that's why the sigma terms disappear. Now essentially what you want to do is that you want to make sure that you are picking your x's and y's in such a manner that this property is maintained, that the local distances, if I and j had small local let's say sort of distances in the higher dimensional space, they are overall maintained even in the lower dimensional space. So look at it from this point of view. So let's say that sort of this probability P, this sort of metric P, it gives you a probability of the point J being picked in the higher dimensional space when a point I was given to you, right? Similarly, the metric Q denotes the probability of point J being picked in case like sort of the point I was given to you in the lower dimensional space. So what we intend to do is the following, that we want to make sure that the probabilities of these two, the metrics P and Q, are close enough to each other, or rather, let me put it this way, that they follow the property that smaller distances are represented equally across P and Q, but larger distances in P can become small distances in Q. That's what we want the structure of F to be, right? Let me just repeat, just in case I didn't make the point. So once we have transformed the problem, the transformed problem looks like the following, that the matrix P denotes the probability of picking the point J given I in the higher dimensional space. The matrix Q denotes the probability of picking J given I in the lower dimensional space. And then what you're doing is that you are defined a metric between the matrix P and matrix Q to make sure that they are similar to each other, right? And coming to like sort of how it should look like, essentially what you do is that in the higher dimensional space, you realize that it is okay to convert distances into probabilities using a Gaussian distribution, whereas in the lower dimensional space, it is better to convert distances into probabilities using a student's t distribution. Now, why is that important, right? And that was the primary contribution, according to me, of this particular t-SNE paper, where they said that in the lower dimensional space, it's very important for the heavier tails to be modeled. So essentially, that's why sort of modeling the heavier tails in the lower dimensional space gives you better results overall in case you were not to have the t-distribution modeling the process of converting distances to probabilities in the lower dimensional space. Okay. And yeah, so essentially sort of restating it, similar points in the input space that you want to make sure that they are sort of converted to similar points in the output space, which is similar points in X get to similar points in Y, but vice versa need not be true. Now, the specific choice of the distance measure, which is F between the two matrices P and Q, is chosen to be KL divergence. Now, KL divergence is something very sort of like fundamental to information theory and machine learning as such. For those of you who know about it, like know the importance and sort of the number of places that KL divergence appears. For those of you who don't, let me explain a little bit more about like sort of what KL divergence or Kullback-Leibler divergence is about. So KL divergence is a concept in information theory or is in machine learning. Machine learning borrowed it from information theory, where essentially sort of given two distributions P and Q, what you're trying to do is that you're trying to come up with a measure of how the two probability distributions compare. So essentially what you're saying is that that sort of if there was a probability distribution P, and if it was to be represented by Q, how accurate would that sort of representation be? And what this leads to is that it leads to an asymmetric distance, because then what happens is that the measure of the distance, in case you were to invert P and Q, in case you were to replace P with Q and Q with P, does not remain to be the same. So essentially this asymmetric distance, what it allows for us to model is that if there was a large probability which was modeled with a small probability in Q, it will result in big penalty, and vice versa, a small probability P modeled with a large a probability in Q would not result in such a large penalty as such. Now, having done that, essentially what you do is that now you carry out a gradient descent method to optimize for the t-SNE problem overall. Now, what you have to keep in mind in carrying out this optimization as such, in the early stages of the optimization, you add a little bit of Gaussian noise to map the points across, and then you gradually reduce that variance in this noise to help the optimization along. This is required essentially to make sure that the optimization doesn't get stuck in any local minima and is able to like sort of overcome them and converge to a global minimum overall. And in typical sort of t-SNE implementations, what is done is that this optimization is carried out several times to make sure that sort of you find appropriate parameters. But the key take-home concept as far as t-SNE is concerned, t-SNE, while it sort of allows you to visualize these high-dimensional data sets into sort of low-dimensional, two-dimensional spaces, it only preserves distances of points which are close by. It ignores points that are far apart, and that leads us to like sort of kind of visualizations that you would see on the right hand side on the slide. So then MNIST dataset is so for those of you who are a little familiar with machine learning, MNIST dataset has been quite popular in machine learning for many years, where the problem was to be able to identify or OCR read digits written by hand. And the idea is that sort of in case these handwritten characters, if they were to be represented in lower dimensional space, how they would look. So and there are various ways of mapping these characters, written characters, into lower dimensional space. Another popular one is salmon mapping. But then with every other mapping technique that has existed out there, essentially has this problem that it is unable to segregate very well these handwritten characters. So in case of salmon mapping, as you would notice that sort of these are quite overlapping as such, but whereas sort of what t-SNE does is that it's able to segregate these out quite well. with like sort of these each of these colors denote the corresponding character being written. Okay. Um, yeah. Okay, getting ahead with the objectives of this module. So what we are going to do is that we are going to learn a little bit more about dimensionality reduction techniques. In particular, we are going to talk about like singular value decomposition, or SVD. We are going to talk about principal component analysis, or PCA, and in addition, we are going to talk about matrix factorization. We are also going to talk about a little bit about like where does one apply which particular of these. We will touch very briefly on autoencoders, which are or sort of the representation learning. But representation learning and embeddings and autoencoders, they are a big area in themselves, and I think that's probably a story for another day. But in this module, we will restrict ourselves to SVD, PCA, and matrix factorization as such. So the motivation behind, like sort of like we discussed earlier also, right? That we are deluged with large amounts of data. We can either see this as a challenge or utilize the most of it. So dimensionality reduction techniques, what they do is that they essentially present us with a way of capturing out information from this large data set as such. That's just sort of the recapitulate of what we have learned till now, right? Some of the applications of dimensionality reduction. So, for example, there are recommendation engines that benefit from this. Essentially, when you say that in a movie recommendation problem, for example, the users are sort of a certain number of types. The movies are of a certain number of genres, and that there is an overlap between the types of users and the type of movies. So there is a certain structure of the problem that we can benefit from. Similarly, in genomics, if we were to try and sort of read the whole gene data, probably it'll get too much. But in case you are able to sort of organize that using dimensionality reduction techniques, it becomes a little bit easier to visualize what exactly is happening, right? And similarly, like sort of for image and voice recognition, for example, as in sort of large social networking companies have this problem of being able to like recognize faces, right, and be able to disambiguate if two faces are the same or not, or of the same person or not. So these kinds of like classifiers for image and voice recognition, they sort of tend to utilize a lot of dimensionality reduction. In Amazon also, like sort of for voice recognition on Alexa and a lot of image recognition that we carry out, dimensionality reduction plays a large role. So for example, for product recommendation, the problem that we are facing is that what kind of recommendations should we show to which user? So in this problem, essentially what you have is that you have lots and lots of users, and what you're trying to learn from is that these lots and lots of users have essentially interacted or purchased or like sort of liked lots and lots of products. But then the question is, how do you utilize that information, right? So your original space itself is very, very large dimensional. How do you reduce the dimension of that space to be able to learn something useful out of it, right? So essentially what you do is that you take your users, you map them onto a smaller dimensional space. You take your products similarly and then map them onto another smaller dimensional space. Now the users and products, they interact with each other on this smaller dimensional space. So this mapping onto a smaller dimensional space, what that does is that it typifies your users and it typifies your products so that you are able to propagate what you have learned from one user to another user of the same type, and what you have learned about product of one type to product of the same type as well, right? So then you learn user affinity to product groups as well. You get to know which particular user belongs to which affinity group. Similarly, you also learn about what the product membership is to a particular product group as such, right? Similarly, in case of genomics, what you are able to do is that you are able to visualize this large gene data onto like a 2D or a 3D map. In this particular case, this is a 3D lower dimensional representation. and that you are able to essentially map out the ancestry information of various individuals, where they sort of like where they came from in terms of their genomes, on a three-dimensional space. That's quite extraordinary, because considering that the kind of information that the genomes they contain, being able to map that onto a three-dimensional space itself is quite remarkable. Right? And similarly, like sort of for facial recognition, essentially the problem is that sort of, can you recognize images of people who are actually the same person? So given a training data set, are you able to build a classifier that's able to recognize people? So in this cases, and if you look closely, I think you may be able to see that there are some people who are wearing spectacles versus not. There are minor variations and so on and so forth. There are variations too in terms of the pose, the lighting, and so on and so forth. Right? So facial recognition is another such problem that can be mapped onto a smaller dimension and then be solved. Okay, so coming on to like sort of, we can start with singular value decomposition. That's our first dive deep topic in this particular sort of subsection. So in singular value decomposition, essentially the question that you are asking is that given a matrix X, which has m rows and n columns, can we represent it more economically? Now this matrix X with m rows and n columns can be sort of originating from a variety of sources. It could be like sort of, for example, the link graph between various URLs. It could be the graph between various users at Amazon, various products at Amazon, and so on and so forth. Okay, so the question being asked is, can the rows and columns of X be expressed as a linear combination of certain basis vectors? These basis vectors are in smaller dimension as such. So if you were to mathematically write this down, this is what the structure would look like. So you have the larger dimensional matrix, which is X, which is in small m cross small n. Don't get fooled by the small m and small n. These are typically very, very large numbers. And what you are trying to get to is that you are trying to get to a representation where these can be represented by very few basis vectors themselves, right? So and you express the matrix X as a matrix multiplication of the matrix U, which is an m cross m matrix, matrix S, which is an m cross n matrix, and then a matrix V transpose, which is an n cross n matrix. Okay, so so the structure of these matrices are that sort of U and V are unitary matrices themselves. The diagonal values of S are singular values, and the columns of U and V are called as left and right singular vectors themselves. Now, the dimensionality reduction actually takes place only when you find out that a lot of these members of S or the diagonal values are actually 0. Okay. Once you find out that many of these are 0, essentially what you would find is that you are being able to represent the matrix X in a much smaller dimensional space. So this is how the matrix multiplication actually looks like, sort of. So you have an m cross n original matrix X, which gets represented in terms of an m cross r and r cross r and an r cross n matrix. And typically R is much smaller than m and n in most applications. Okay, so that's why sort of you can count the number of parameters that exist. Sort of there are m times n parameters that exist here. There are m times r plus r square plus but these are sort of the only diagonal matrix are diagonal elements are non-zero, right? So there are r elements here actually, and then there are r cross n or n times r parameters sitting here. Okay, so this reduction in parameters is the one that leads us to an SVD application. So in case we had, let's say, sort of a all-one matrix, an all-one matrix, for example, as a toy example, it would get represented as so in case you have an m cross n all-one matrix, it would get represented as 1 by square root m of a unitary matrix of this type, a single element of square root mn, and 1 by square root n of unitary matrix transpose. Okay, so what SVD does is that it allows us to identify block diagonal structures. So in case a matrix has a block diagonal structure, then SVD can help us recognize that. And I'll give you some examples of what that block diagonal structure looks like and how it is beneficial. But mathematically, sort of like it is expressed as, like we saw earlier, as a multiplication of smaller matrices U, S, and V transpose. Okay, so let's say that sort of you had a problem which was related to text. So you had a textual problem where what you you had the document numbers represented on the x-axis. So this top row, if you see, notes down the document numbers, and you have individual words. So essentially these colors or the darkness of a particular cell is showing you how frequently is a word occurring in a particular document, right? Now, essentially the question that we are trying to ask is the following: is there a certain substructure to these documents? Are the documents talking about the same topic or not? So essentially an SVD operation on this term document matrix, it leads you to this. So which is essentially what you have done is that you have rearranged the documents and you have rearranged the words. But essentially in doing that, what you have realized is that there are certain documents which are talking about only these words. So most of their weights are on these ones. Whereas then there are other documents which are talking about another topic and so on and so forth. So in general, what this does is that it allows you to represent the much larger term document matrix in terms of diagonal elements and be able to recognize if there is a substructure sitting there. Okay, so essentially this is the operation that essentially leads us to what is called as a latent semantic indexing analysis. It was proposed quite some time back in 1990s, about 30 years ago now. But as in latent semantic analysis still gives you topics which are quite readable to human eye, and we will see some examples as we go through the presentation. Coming on to how you compute the SVD. So the SVD computation, what you have to realize is that the SVD computation, if you try and do that on the basis of the original definition itself, can get a little convoluted. But in case you realize the structure, which is that for a given matrix X, that if you were to take X times X transpose, so essentially it turns out to be like U times S square and U transpose. Similarly, like X transpose times X becomes V S square times V transpose. So what happens is that that your USV become like solutions to an eigenvalue problem, and then and these are symmetric matrices themselves. X transpose X is a symmetric matrix. So essentially what you are able to do is that you are able to convert the SVD problem solution to an eigenvalue identification problem, right? So that eigenvalue identification problem is something that has been well studied. We know efficient ways of carrying it out, and I'll lead you through one way of computing that. It's called the power iteration technique. There are other techniques available for computing eigenvectors. and eigenvalues, quite efficient, but essentially trying to give you a sense of how this can be done fairly quickly. Okay, so the power iteration technique, what it does is that it sort of goes through eigen values one after another. So what it does is that in step one, it tries to identify the top eigenvalue, and then based on the top eigenvalue identification, it tries to identify the next one, and so on and so forth. So so then once you do that with high probability, you converge to like sort of the eigen vectors that you were looking for in the first place. Okay, so in the power iteration technique, what you have to realize is that that sort of u is a vector in like sort of r power m space, and that what you have to do is that you have to essentially realize that v is the xx transpose times u. Okay, so what you do is that you try and find the eigenvalues, sort of turns out to be the square root of u transpose x transpose u. And once you have then figured this out, right? So then what you do is that sort of you use a numerical technique to get to this particular value. And once you have realized this value, what you have to do is that you have to then compute the next version by realizing that the next eigenvalue is perpendicular to this computation. Okay. Next, we come to principal component analysis. In principal component analysis, what you do is that you have a data matrix which is m cross n in structure, and what you are trying to do is that then you are trying to identify a low dimensional space representation that sort of essentially conveys the maximum information about this matrix as such. Okay, so what you're trying to do is that you're trying to say that is there a smaller dimensional R, and in case like sort of I had only that much space to represent my matrix or the information about it, can I still have minimal information loss? Okay, and I'll show you like sort of the examples also of what PCA can achieve in terms of compression, image compression, and others interpretable stuff. Okay, so PCA as such, if PCA is actually like the SVD of centered data matrix X. So centered data matrix X is nothing but like sort of you take take each mean of the matrix X and you just like subtract the mean from each row. Okay, and what you're trying to do is that you're trying to represent in principal component analysis, you're trying to say that look, is in the first R columns of U, and the first R rows of V are significant. The rest all is noise, right? So in terms of S, which is again remember that this is a diagonal matrix as comes out from SVD. So your most of your signal is actually sitting on the top part, right? On the top, like sort of top diagonal elements. Yeah. So like I said, the columns of U are principal vectors, and then sort of the what you can do is that you can take a any matrix X and then project to a lower dimensional by just multiplying it with U transpose. It leads to a lower dimensional X hat representation, and in case you had X hat, you could like sort of reconstruct it back to the original matrix by trying to sort of pre-multiply it with U. This becomes quite important in things like signal processing, where you are or sort of like, for example, image compression, where what you are trying to do is that you are trying to sort of compress the image down and then be able to still compute the original image. Principal component analysis becomes quite important for us even in machine learning, when you're trying to figure out like is the overall structure of the problem in a much lower dimensional space. I will show you an example of principal component analysis, or I would say in this particular case, matrix factorization done. Matrix factorization is a specialized case of principal component analysis when you don't have the entire elements of the matrix being available, and how that is useful for us in machine learning. Okay. But then coming to like sort of the question of variance, or the question of signal as such, please remember your sort of learnings from math back in terms of your studies on eigenvalue and eigenvector analysis, that your principal component actually is the one, or the principal eigenvector direction is the one which has the maximum sort of variance, so to say, and sort of in terms of diagrammatically, this is how it looks like. So in case you had this particular point cloud, your principal eigenvector would be the one which would be pointing in a direction which is on along sort of maximum variation. So sort of this is how the principal eigenvector would look like, and correspondingly for PCA, that's the direction of your principal component as well. Similar to the eigenvector sort of analysis, the next eigenvector is orthogonal to your first eigenvector, and similarly in PCA the same thing takes place. So next what we will do is that we will look at sort of how PCA when carried out on an image looks like, as in how much compression of a particular signal can be carried out. So think about it this way, that let us say that you have been given an image which is of this nature, right? So you have this beautiful image of a butterfly which is like sort of which is 372 by 492 pixels. That's the original image. And essentially the operation that we are carrying out is that we are dividing this overall image into a grid of 12 by 12 pixels. Okay. So your 12 by 12 pixels is in sort of, think about it, any sort of portion of the image gets divided into 12 by 12 box. And then what you do is that is then you think about that 12 by 12 box into as a 144 dimensional vector. Okay, so this is just giving you that intuition that is in sort of your 372 is 31 times 12. So in sort of you have 31 of these 12 by 12 blocks which are stacked up in this manner, and similarly you have 41 of these stacked here, right? So as in overall you have these 144 dimensional vectors, 31 times 41 of those. Fair? So now as far as PCA is concerned, so in case you were to for example carry out the principal component analysis and do what we call as a reconstruction error. So essentially, let us say your original matrix was X, and like we talked about earlier, that you can reconstruct this matrix. So U transpose X gives you X hat. Remember from a few slides ago that U transpose X gave you X hat, which was in a much lower dimensional space. And this graph is showing you that in case the X hat was like sort of of let's say only 10 dimensions, then how much of your matrix would you be able to reconstruct, like how much information loss do you have. And let's say that this is our reconstruction loss metric. Then as your PCA dimensions increase, like sort of once you increase it like sort of beyond 100, of course, like you have zero loss as such. But it is quite interesting to look at that even with only a few dimensions, which is 10, you are able to reconstruct this image quite well, actually. Right? So in sort of your, for example, your 144 dimensional picture, once it's compressed to like sort of 60 dimensions itself, it sort of looks like this, and then further reduced to 16. I mean, sort of, then the human eye can very easily figure out that this is still the picture of a butterfly. I mean, even at a 6-dimensional image as such, it's quite sort of understandable. Okay, for this 6-dimensional image, for example, the principal components look like this. The individual components may not be like sort of quite readable, but they are able to reconstruct the image back for you. Okay. Actually, in the next subsection, I'll show you an application where the principal components themselves are quite readable, and but you have to apply a certain structure for them to be readable. In this particular case, we didn't apply any structure for the principal components to be readable. But in case you want them to be interpretable and readable by the human eye, then you have to apply a certain substructure to it. Okay. Now there is a more, I would say, modern view of principal component analysis, which is the encoder-decoder view of PCA. So now the encoder-decoder view of PCA is quite important in current state of the art for machine learning, because essentially sort of autoencoders or the encoder-decoder architecture as such is used everywhere, essentially. Like sort of all your deep learned models, essentially sort of which are popular today, use this entire mechanism of getting to an embedding space and then using the representation learning as your bootstrap for doing a variety of tasks, your multitask learning, your zero shot learning. All those things use some sort of a representation learning and utilize that, right? So however, sort of while PCA is a linear transformation carried out through these matrix multiplications, the autoencoders themselves are non-linear in nature, because then sort of the encoders and decoders are non-linear neural networks in themselves. And the more complex the neural network gets, the better representations it can learn. So then transformers, for example, or multi-layer sort of transformers tend to be very, very complex models in themselves, right? But that's what we would talk about, sort of the autoencoders and sort of multi-layer transformers and all. That's probably, like I said earlier, that's a story for another day. Yeah, so sort of for representation learning in autoencoders, essentially what we do is that we build these autoencoders and then we back propagate. So what you're trying to do is that you have the original matrix or the original data itself, and then your encoder encodes it into a smaller dimension, and then the decoder tries to reconstruct it back. And then what you try and do is that you try and minimize this reconstruction error, so to say, right? At the time that you are able to minimize this reconstruction error, gives you an efficient representation in the smaller dimensional space as such. Okay, so coming to matrix factorization. Now, matrix factorization is quite a unique sort of, I would say, specialization of principal component analysis. Matrix factorization sort of takes the idea that let's say that you had an incomplete matrix X. So think about it this way, that in case you have the problem of recommending movies to users, right? Now the user's movie matrix is never complete, right? As in sort of, so in case someone has not watched the latest, like sort of Doctor Strange movie, the Multiverse of Madness, that's an incomplete information that you have. You cannot assume that if someone has watched the movie, you cannot assume whether they would have liked it or not. It's just pure missing information, right? So then sort of so from a recommendation problem point of view, of rather than treating that as a 0 value or as a 1 value and trying out certain imputation, essentially what you do in matrix factorization is that from like sort of first principles, you assume that value is not available to you as it is, right? And matrix factorization essentially tries to do the same dimensionality reduction to lower dimensional matrices with this structure of X with incomplete information. And this particular operation or of identification of these lower dimensional matrices in case of matrix factorization is also called as identification of latent factors. And like I said, sort of this matrix factorization has been used successfully in multiple things like sort of recommender systems, tomography, and so on and so forth, to be able to identify what are the like essential structures in sitting in problems like these. Now let's come to the discussion on learning of these latent factors. Think about it this way: that you're given a problem of user cross item interaction, right? Essentially, sort of the users have bought certain items, and then let's assume that this is the interaction matrix that's giving you an idea of what is the rating that a user has given a particular item. So in this particular case, the user 3 bought an item 3 and gave it a rating of 3. Whereas similarly, the user 2 or user 4 sort of gave an rating of 4 to item 2. But essentially, user 3 has never bought an item 4, right? So we don't know what the rating is that the user 3 would give. Now, very early versions of ML models, what they did was they would use this this structure as an imputation problem. They would like sort of try and impute these missing values and then try to carry out a normal PCA analysis, only for later researchers to realize that it was probably better to just assume in matrix factorization terminology that these were essentially missing by themselves and then treat them as missing for the overall computation. So again, you would realize that this problem has a very similar structure to SVD, PCA, right? Sort of you have this smaller dimensional sort of matrix U, R, V, again very similar to the structure that we have seen till now. And essentially the way you try and model this is by saying that sort of for a user I and item J, you are trying to learn a model which is of this nature, that your rating of item J by user I is essentially a multiplication of U with V, but there is a bias term that the user has and there is a bias term that an item has, essentially, right? And much more complex sort of structures can be learned in case of matrix factorization as such. But essentially this is the structure that you're trying to learn, and this is the overall setup. Now the question is, how do you learn these particular parameters, right? So instead of how do you learn your overall like sort of parameters for these equations, so to say. So let's say that sort of you have been given this particular model. For now, we assume that the model that we are trying to learn is simple, an interaction term, and then bias terms for the user and the item as such. One way of solving this is through alternating least squares. Essentially, what you do is that you first learn the user matrix, and then you try to learn in the next step you try to learn the item matrix and so on and so forth. But there is a sort of probably an even easier method to do this sort of simultaneously, to be able to carry out these updates to users and items estimates in a single go as such. Okay, now and this alternating least square sort of you can carry out that optimization using stochastic gradient descent, because it adapts very well to online setting, where you are able to achieve like very quick updates to these estimates, and then update them as you go along based on the latency requirements that you have. Okay, so in trying to do this, like I said earlier, the updates, and what you're trying to do is that in one step you're trying to do the updates to you in step 1, and then given a particular u, you try and estimate what v would look like, and sort of then u, then v, and so on and so forth, giving you the alternating v squares update structure to it. Okay. So then, just to be like clear about it, like sort of first you fix the UIs, and then you, given the UIs, you solve for the V's, because the ratings are observed, right? You already know what the ratings are, and then correspondingly, once you have realized the V's, you back propagate, and then you try and estimate what the U's look like. Okay, and there are versions of this where you can update the user and item representations simultaneously as well. That sort of, those are much faster versions of achieving, I would say, sort of the optimized estimates of U and V themselves. Okay. And like we discussed earlier, this overall structure as such allows you to take side information into account. Till now we have only talked about using the bias terms for users and items. You could also bring in other features of users and items into account. For example, if you wanted to say that sort of, let's say the number of movies a user has watched, let's say if that is a predictive feature for the user giving a particular rating to a particular movie, or the number of products a user has bought, that sort of is somehow predictive of the rating that the user can give a particular product that he or she purchases next, then that can be used as side information into the model as such. Now there is a very specialized form of matrix factorization called as non-negative matrix factorization. Essentially, where what you say is that, look, I want my individual latent factors to be interpretable in nature. For these latent factors to be interpretable, what you do is that you impose a restriction on them that all your, for example, your U's should be all greater than 0. Okay. So, for example, if you were to carry out NMF on the facial recognition data or the facial data, this is how it will look like, and potentially you can see like sort of how eyes are coming out at certain places, certain nose related features are coming out. Overall, like sort of this is becoming more and more an interpretable substructure. Like earlier I showed you the 6-dimensional output of the PCA vectors. They were not very interpretable to the human eye. In case of non-negative matrix factorization, you can see these latent factors become more interpretable. Let's look at one particular example of a textual problem where we can actually see how these latent factors can be interpreted. Okay. So let's say that sort of you have been given this particular problem where you have a set of documents and you have terms which are present in those documents. This is your X overall that we have been talking about, right? So in this particular application, your documents were reviews of products, and your terms are actually sort of words that people have used in each of those reviews. So essentially what you're trying to find out is what are the aspects of products that various people are talking about, and is there a substructure to that. So you take this document cross or term cross document matrix in this particular case, and then you try to break it down into these parts that sort of the first part, or U, becomes your term cross topics, and then the V part becomes your document cross topics, topics cross documents, whichever way. Yeah. Okay. So once you carry out this process on, for example, the reviews data set, this is the output that you achieve. Like sort of these are very, as in you would notice that these are very readable topics, so to say, because this is part of non-negative matrix factorization, right? You have made sure that individual terms can only contribute either positively to a topic, or like sort of their weights can be zero. They can't negatively contribute to the topic as such. So many of these, for example, are very, very readable. For example, a topic on delivery talks about delivery time. It talks about like sort of the number of times somebody has to return it, if the packaging was any good or not, and so on and so forth. Like similarly, like sort of money topic talks about is it a waste of money, is it value of money, was it paid by cash or not, and sort of were the refunds easy or not. Similarly, sort of there are topics on cloth. Is the cloth how does the stitching of the cloth feel like? Is this smooth? Is this polyester? And so on and so forth, right? And within these topics themselves, you can try and figure out what are the weights for these individual terms within the topics, right? So that gives you an idea of how you could use non-negative matrix factorization to be able to realize what your customers are talking about in reviews, right? So overall, in conclusion, like sort of from this module, we talked about like singular value decomposition, PCA, and matrix factorization techniques. We talked about non-negative matrix factorization. We saw some examples of where these can be useful. We were able to also discuss like sort of some of the algorithms that exist to solve these. And the current state of the art is that these problems can be solved for very large scales, and they are quite sort of efficient tools that exist out there. My recommendation to you would be experiment them in your next ML model problem that you pick, in the next problem that you try to solve, the next ML hackathon that you attend. Experiment with these. They may be able to give you a substructure that is much easier to solve. Many of these, like the matrix factorization solution to recommendation systems, is actually the state of the art for giving movie recommendations, right? And just to sort of revise what we have learned, like sort of in terms of the conceptual items that we went through. PCA is your singular value decomposition of a centered matrix. A centered matrix, what you have done is that you have just taken the row of the X matrix and sort of subtracted the mean out of that. Your matrix factorization is decomposition of an incomplete matrix where the individual elements are not completely observed. There is another like sort of decomposition. Tensor decomposition is when you have higher order matrices involved or tensors involved. And my overall recommendation would be that sort of please revise your linear algebra 101 again. It is probably more useful than what you thought when you first studied it. Thank you so much for your attention. It was great presenting this topic of machine learning, which is very close to my heart as far as the overall area of ML is concerned. Thank you so much.